Okay, it's 6:09 now, so I guess we'll start. Let me try sharing my screen, see if this works. It does. Okay, just a couple things. If you want to ask a question, feel free to. You can either text in the chat or you can unmute yourself. Don't unmute and start playing shit. I do have soundboard disabled because the first time I did a tutorial, you guys were spamming. So if someone's spamming soundboard and it's causing too much of a problem, just say it. But yeah, please don't be a soundboard. So we're just going to be covering basically all of the practice midterm that was posted, plus a little extra. I have a couple extra questions that are harder than the ones on the midterm, just from either posted in chat or I found elsewhere as practice. So we'll be going over op amps, Bode plots, and what's the third one? RLC circuits. Those are three things that's going to be on the midterm, right? So, can you do some second order ones? Yeah, definitely. We're gonna. So, do you guys want to start with the second order one? What are we feeling? Starting with second order, Bode or op amps? AC. Hoop amps? Seeming like mostly. Seems close, but it seems op amps. You know, I'm just gonna copy it because this is from one of the editions in the textbook. I don't know which edition it is. What software do I use for notes? I use RNote. It's very nice. I use it all the damn time. RNote, like that. So this is the circuit. This is a double op amp AC circuit. This is probably as hard as it's gonna get. Yeah, there's not much to say here. We have a voltage source, two op amps, and a lot of negative feedback. So the first thing that we want to do is obviously convert everything into AC and combine parallels. So this here, converting into AC, we're going to get 5 with a phasor of 0 because it's cosine. Remember that if it's sine, we're going to have to, it's going to end up 5 with a phasor of 90 degrees. Or is it negative 90? Man, I already forgot. Negative 90. Negative 90. Big negative 90. Remember that, because you might get a sine, and if you mess that, you're going to get everything wrong, like I did there. So with that, we know that this capacitor is going to turn into, that's 1 over JWC. What if it was 5 sine? Yeah, so if you had 5 sine 10 to the AT, that would just convert to 5 with a phasor of negative 90. If negative 5 sine, that would be the exact same thing here, but if you put this into your calculator, I actually don't think it will let you. You have to do... I don't know why they're very annoying about this. Yeah, it won't let you do this. You have to do this. And if you do that, it's just going to end up as 5 with a phasor of 90. Yeah, for cos, it's 0. And likewise, if you have negative 5 of cos, if it's sine, it's always negative? Yes. If it is sine, it's always going to be negative 90. It's only if you have negative sine, it would be 90. Did I start the tutorial already? Yeah, we already started. You're late. Get out of here. Late people aren't allowed in here. Okay. Cosine. What if it was cosine? I assume you meant 10 cosine t plus 90. That's just going to be an addition on top. So it's going to be 10, 0 because it's cos, plus 90. Like that. So for anything that's going to be amplitude cosine of some omega t plus your phi. It converts into amplitude with a phasor of phi. If it's sine, it's going to convert into A with a phasor of negative 90 plus phi. You need to know that. Again, if you mess that up, your answer is going to be wrong. Yeah, I don't think I can mute soundboard for everyone. You just have to do that on your end. But if someone's like really abusing it, do tell me, because I can just remove them. Okay, so back to the question. So now we gotta convert everything into AC. So we have 1 over JWC. If you put that in your calculator, 1 over J, which is I times W, which is 10 to the power of 3, times C, which is 0.1 micro, and micro is times 10 to the negative 6. I would hope you all know how to use complex in your calculator by now, and remember to put it in what do you call it? Degrees. Don't put it on radians. You're wrong. So 10,000 J. And likewise, this one here is going to convert into negative 5,000 J. There you go. So after we have this, we can combine these two. They're in parallel. So the combination is going to be 1 over Z plus 1 over Z2, Z1, Z2, to the power of negative 1. So we're going to get 1 over 20,000 plus 1 over negative 10,000 J to the power of negative 1.
You mind if I ask a question related to second order? It's just a problem I'm doing right now.
Sure, if it's quick.
Yeah. Yeah, so it's I don't know if I can screen share or I can just send you a DM, but there's this problem, and they just assume the polarity of something with KVL, and I'm a bit lost to why that's the case. Like I was like, okay, let me just assume it the other way, and that's wrong. So
it depends. Usually, if you have a KCL circuit, for example, say if you have a capacitor like this is the positive, this is the negative end, the current is assumed to flow from positive to negative, because that's what the positive and negative means, right? I am going to combine the resistors. I'm just responding to this question. Likewise, if you have an inductor, you have the positive and negative ends, the current is assumed to flow downwards.
Can I just send you a picture of my question? Or?
Yeah, sure. But I'll get to it later, because I don't know
Yeah,
if I can...
Yeah, no issue, man.
Yeah. The Z thing? This is for AC. So for AC, if you have two impedances, we call these impedances, in parallel. So impedances are just going to be some resistance plus reactance, like that. C plus DJ. This is Z2, and this is Z1. So the formula for combining it in parallel is going to be 1 over Z1 plus 1 over Z2 to the power of negative 1. This is the same formula as resistance. If you have two parallel resistors, it's going to be 1 over R1 plus 1 over R2, all to the power of negative 1. We make this differentiation for Z because you cannot do the same for resistance and a capacitance like this. You can't just add the Faraday and the where Z2 come from? Here. So okay, here, let me try and take the middle step, because I skipped a step here. So the capacitor has a reactance of negative 10K joules. So if I draw it out, it's going to look like this. We have 20,000 on top, and then we have a capacitor here. Well, we'll draw it as an impedance here of negative 10,000 J. What is the objective for this question? It's to find VO. So this is the circuit we have right here. And so to combine them, it's just going to be 1 over Z1. We'll take this as Z1. Plus 1 over Z2. We'll take this as Z2. All to the power of -1. I hope that makes more sense, because I was sort of skipping steps. My bad. Yeah, it's from the capacitor. So we're combining these two here. So, yeah, no worries, no worries. So, combining them together, we get that this is 4,000. Actually, it's 4K minus 8KJ. Is the total impedance of that 4 minus 8I? You're off by a total of 1,000. Yeah, there you go. 4,000 minus 8,000. Let me just transfer this to another page so that it's not lost, but it's not in our way. So, we can now simplify the circuit. And this is something that I like to do. I know that I have a friend who doesn't like the way that I do this, but I think it helps you understand the circuit a bit better. When you have an op amp like so, when working in ideal circuits, you can convert this. Is that microfarad? Yes, it's micro. They're both in micros. You can convert this, and this is going to be the negative pole, this is going to be the positive pole, and you draw this dashed line here to represent that the difference in voltage is 0, but there's also no current across. And then you have your dependent voltage source come out. I find that this makes things a lot easier to understand, because now you don't just have this black box that we call an op amp. But over time, you will get used to the op amp. You won't have to keep rewriting it. So let's rewrite the circuit. The next thing that I like to do is I like to split up ground, because ground gets a little too big for my tastes. Again, it's the same circuit. I'm just redrawing it a different way. You can draw it just as is, but I believe that this will help you understand it. If it doesn't, then just tell me. We'll go back to the normal way. So we have our impedance block up here of 4,000 minus 8,000 J over our op amp. So this is going to be... This is probably the hardest question you could conceivably get. I don't think it'll be on the exam, but it's like, it's possible there is. I forgot how long the midterm is. How long is it? Let me just move this down here. If you can rewrite the circuit to be nicer for you to understand, do it, because it just makes your life easier. Again, you have another impedance here. This is going to be -5 kJ. And then you have our second op amp here. Over a 40K resistor. To VO, which is also connected to ground. Do you guys is there anything I sort of went too fast that's hard to understand? Okay, I'm gonna assume that everyone sort of gets what's going on here. So because of this, nar. Wait, how is it negative 5 kJ? Here. It's this capacitor here. Yeah, it's the same circuit, it's just redrawn. Actually, I'm gonna write on the side the sort of way of doing op amps that I do, because I feel like someone will just look at the thing and get a little confused. So negative, positive. Delta V is equals 0, I is equals 0. That's our ideal assumption. And our dependent. Did the 20,000 resistor just get converted to 4K? Yeah, it's because it's in parallel. So if you look here, we have 20,000 on the top and negative 10,000 J on the bottom in parallel. And using impedance reduction, we can just turn it into a single impedance block of 4K minus 8KJ. Can you explain the negative 5KJ? Yes, that is this. It's this capacitor here. Here, let me draw the lines here. It's this capacitor here, and you just do 1 over JWC. You'll get negative 5KJ. So, at this point, you can sort of guess, guess what's going on here. So the current's going to come up and down into here. And where was I doing this? Just want to make sure I'm not doing anything stupid. Actually, you can't assume this. So now we can, okay, ignore what I was saying there. Now we can just do KCL. Negative 1 over 0.2. Oh, you're doing the JWC. Yeah. Yeah. Now we can do KCL. Whenever you have op amps, you do KCL on the negative input. So that's right here, because it makes everything a lot simpler. So let's define our V's. So this is going to be our op amp, our amplifier 1. Let's call this our amplifier 2. Let's just call this V. Actually, let's just use letters or numbers. So it's V1. This is going to be V2. This is going to be V3. And this is going to be V4, which is also VO. Where is 0.2 from? Yeah, there you go. So we want to do KCL around negative op amp input. Makes everything a lot easier. So let's start with V1. So we have two inputs. We have this one over here, and we have coming out here. You can assume the direction, it doesn't really matter. You know how KCL is, you should be able to do this by now. So that's going to be from 0 across our voltage source of 5 with a phasor of 0 degrees. So we can just simplify that to 5 minus V1 over 10,000 ohms. That's coming in, and coming out is going to be V1 minus V2 over 4,000 minus 8,000 K. Never knows how I got that, right? It's just KVL. Now, the nice part, actually, I should be doing this in black. I love KVL. The nice part is we know that the difference here is going to be 0. This is connected to ground. What does that tell us? V1 is 0 volts. So we can cut that out. We can cut this out. We can cut the 0 out because 0 is 0. And now what we are left with is 5 over 10,000 ohms is equal to negative 1 over 4,000 minus 8,000 K V2. you should know how to solve this. So we get that V2 is going to be equal to, I am too lazy to do all the math, it is -2 plus 4j. You can also write this in phasor. As always, phasor and rect are the same things, just written different ways, but this is a lot nicer than the phasor representation. So now we can move. So now we know V1. We know V1 here. We know V2 here. And we need to know V4. So again, we're going to do KVL around V3 because this is the negative terminal of the op-amp. Very easy. Once again, we're just going to assume that the current flows in this way. It doesn't really matter. And that it's going to come out this way. Ideal amp VA is equal VB is equal 0. Yes. So if you don't remember, the ideal op-amp tells us that the voltage difference is going to be 0 and the current is going to be equal to 0. That's pretty much all it's going to tell you. Is that 4K minus 8KJ? This here? Yes. If you're talking about this, no. This is 4,000 minus 8,000J. Why did I cut out V1? Because V1 is connected to ground. If you look here, this is ground. And remember the properties of an ideal op-amp. Across here, there is no voltage difference. So if we know this is ground, this is 0, then V1 is going to be 0. I know. Because of that, it makes doing the voltage around that negative input very easy, very nice. So this is all that the ideal op-amp will tell you. And you will remember how I blew it up into this connection here that tells us that there's no voltage across, no voltage difference. And we have our dependent input. We don't know how much volts this is outputting. We can't figure it out just from the ideal op-amp. So that's what we have to find out through other means. In this case, KCL. Stupid question, but where did you get the 0 in 0 plus 1 minus V1? Okay, so how KCL works is that you start at the voltage you're coming from, you add any voltage sources you pass by, and then you subtract where you end up. So we started at ground, we added the voltage source because, sorry, we came out of the positive end of the voltage source, so it's plus 5. If we were going the opposite way, it'd be -5. And then we ended up at V1. So 0, where we started, plus 5, the voltage source we went through, minus where we ended up. No voltage source, you remove that. If the voltage source was flipped, it'd be -5, so on and so forth. Can you post a screenshot of what you have so far? Sure. Let me just copy this. Okay. So now we are going to do KCL again over the second voltage node. So this is going to be, let me do black again. So we're starting at V2 and we're ending up at V3 over an impedance of -5 kJ. And that's equal to, coming out, it's going to be V3, we're starting at V3, minus where we're ending up, V4, over 40,000 ohms. And once again, we can do the same thing we did here. This is connected to ground. The voltage difference is 0. So V3 has a voltage of 0 compared to ground. We can cut that out from our equation. And now we can, once again, simplify this. It's going to be V2, which we know, over 5 kJ is equal to -40,000 ohms. Sorry, -1 over 40,000 ohms. V4. Isolate for V4. You know how to do that. And what we'll end up is, did I do it here? Yeah, I did. We will end up with 32 plus 10J. I actually can't read my work. I don't know if that's 16 or 10. Let me try actually calculating it. That's going to be negative 40,000 times, what is V2? V2 is negative 2 plus 4J over minus 5,000 J. 69? I can't even read my own damn handwriting. 16J, and I'm going to correct that in my notes. 16 with a big, can't swear. Where's my, there it is. 6. There you go. And now, what is V4? V4 is our VO. So, there you go. Our VO. And obviously, we don't represent voltage in rect form. We represent it in phasor form. So turning that into phasor form, we are going to get 36 or 35.7 with a phasor of 26.6 degrees. And we got to convert it into time domain. So we always use a cosine for it because it's just easier. So VO as a function of time is 35.7 cosine of r omega, that's 10 to the 3 t plus 26.6 degrees. There you go. I've never seen an easier representation of complex op amps. I know. It's when it clicked for me to draw op amps this way, it just became easier for me to understand. I don't know if that's just a me thing, because I know a friend of mine really disagrees with how I write the op amps. You know who you are, probably not watching. What is 32 plus 16J? That is V4. Sorry. I did not write that. That is V4. Is it? No, it's not him. It's someone else. Dox him. I'm not doxing him. But he has helped me with this tutorial, man. He has a high. Actually, I shouldn't say that. Okay. So now we have solved probably the hardest op-amp question you're gonna get. I do not conceivably see how you're gonna get a harder op-amp question than this. Yeah, I don't think I missed anything. Let me think. It gets harder if it's not ideal. Correct. If you are forced to do non-ideal, it gets a lot harder. But in that case, you can literally just replace the op-amp with the information you're given. And at that point, it's just regular KCL and KVL. So if you're able to do KCL, KVL, like in ELE302, you should be able to do it. Can you do a quick rundown on your op-amp drawing? Yeah, sure. I'm just going to write this here. My method of op-amp drawing. If you have so let's just label this A, let's label it B, let's label it C. Can you do the extended version of the pic the dude sent? I'm not sure what you mean. Wait, sorry, but can you like fully draw this in my own style? Okay, yeah, let me just draw how, like fundamentally how I draw it. So this is going to be, you have your A here, and you have your B here. But that smoke detector beam, it was not. I have it's air conditioning. I have to keep the room closed because I'm talking very loud and there are people in the house. So it gets hot in here. That's a crazy statement. I'm not repeating that. So let's just see here. So that's my way of drawing the op amp. So let me just move that a bit down. So for example, like you gave here, let me draw this in my style, quote unquote. So you would have the voltage source here, and you see it goes into the op amp, the A section. And now you connect that to the B. So this is the positive end, this is the negative end. Oh. And now we're going to connect the what you call dependent thing here. What does the dotted line mean? The dotted line means that the difference in voltage is 0 and the current across is 0. So it's kind of a mix of the open circuit and the closed circuit. Yeah. So like this, bring it out here like that. You have your this part here. You have your op amp generator here. And let's just connect this part to ground. And once again, that output goes into another op amp. This negative part is connected with a 50k ohm resistor to ground. A 200,000 K resistor combined with a dependent voltage source from here. Yeah, so that's going to be positive end. This is going to be negative end. You connect that to ground. You could obviously make this simpler. You could try turning this around, but I like to keep these vertical, so you know that they're not really connected. You know what I mean? Can you screenshot real quick? Yeah, sure. It's gonna be part of the document afterwards, so. There you go. That's all there is to it. And I like to split up the grounds because it makes your circuit simpler. You realize internally that you don't need to worry about this bottom part here. This bottom part here is completely irrelevant, pretty much. That's it. So I think that's good enough for op amps for now. Let's move on to what should we do now? Second order RLC or Bode plots? Okay, the friend in question just texted me, I'm watching. Unlike this. Second order? Sure. Let us do second order Bode plots. Or sorry, wait, booty plot. Bode plots are second order. It's split. Does the op amp basically turn into an independent source? It turns into a dependent source, but we just, yeah, it kind of acts like an independent source that we don't know the voltage of. So you can see it that way. Let's do Bode. Let's just get it out of the way because Bode is, it can be surprisingly hard, but in actuality it's not really that hard. So I'm going to be doing the hardest Bode plot question from the practice midterm. I'm just going to copy it because I am not drawing the graph without, you know, a semi-log graph behind it. Let me zoom in so I can actually know. Actually, yeah, here we go. So draw the Bode plots, both magnitude and phase plots for this. So here's our magnitude here. And here is our phase. I'm probably gonna have to start moving it down a bit. Let me move this down preemptively. There you go. Don't we have one on D2L? Maybe. Would they cut marks for doing op amps this way? I see no reason why. It's just redrawing the circuit same way. Yeah, you're still doing the same circuit. You're still doing the same stuff, so they won't cut marks for you from that. Okay, so draw the Bode plots, both magnitude and phase plots for H, JW is equal to this fun stuff. Question, how many people actually have an idea how Bode plots work? Are we going into this like knowing nothing whatsoever? Or you kind of get an idea, 0? Okay, I'm going to start from 0. Actually, I'm not going to explain what the point of the Bode plot is because I don't entirely understand it either. I forgot. But I will tell you how it works. So the Bode plot is a little special than most other plots because we do it in a logarithmic scale. Can someone send a screenshot of the graph? Yeah. Here you go. 1 second. Let me copy directly from the thing here. So that one there is the phase. This one here is the magnitude. Yeah, the prep midterm is on D2L, so you can just get from there. So Bode plots work on a logarithmic graph. If you look here, you'll see this is 0.01, this is 0.1, this is 1, this is 10, this is 100. It doesn't increase linearly, it increases exponentially. And each one of these points here represents 1/10 of the way there. So this would be 0.2, 0.3, actually it's either 1, 2, 3, 4, 5, 6, 7, 8, 9. And likewise with 10, it's going to be 11, 12, actually no, it's going to be 20, 30, 40, 50, and so on. And for 100, you're going to get 110, sorry, 200, 300, and so on. That's how it works. That's why the points look a little funky. And so we use semi-log graphs. I think they're called semi-log graphs. I'm not really sure why to draw the Bode plots. Okay, so for Bode plots, you're going to get an equation such as this. So in this case, it's 128.205 JW over JW plus 1.538 JW plus 16.667. So crazy. I'm not even going to comment on what was posted there. Actually, I'm not really sure why I rewrote this. So what we like in Bode plots is we like terms to be in JW over some z, some number z plus 1. All of your formats should be in either this or just JW. So you'll see we have JW in the front and we have not the correct formats on the bottom. We need to transform those. How do we do that? Division. This is algebra. You should know how to do this. So we are going to divide all of this by 1.538. We're going to take out the 1.538. And likewise for here. So let me just rewrite this. Erase all of this, screw it. And we're also going to bring out this constant in front. So we're going to get, actually not yet. So we're going to 128.205 JW. Let's put that in brackets so we know that this is one of the terms we like. Oh shoot, I shouldn't have erased that part on the right. good terms. JW or JW over Z plus 1. And on the bottom, we're going to pull out 1.538. So we're going to get JW over 1.538 plus 1 times 16.667 times JW over 16.667 plus 1. So now we have put our equation in terms that we like. And we can simplify this further. So that's going to be 128.205 over 1.538 times 16.667. Our constant is going to be 5. 5 JW over all of this fun stuff. I don't know how to draw straight lines. JW over, you know what, screw this, 1.5 plus 1. Don't do that on the midterm, but it doesn't make like any difference at all. So I'm just gonna skip it. Rounding for speed. Do not do on midterm. Okay, so now we have our Bode formula in a form that we like. What does it? Where does 5 come from? Here. So here, let me just put that in between. 128.205 over 1.538 times 16.667 is equal to 5. So, what does this mean? JW. So, okay, so let me see how I was gonna answer this because I had forgotten. Right. So the formula to plot this out is going to be 20 log of this whole equation. And I'm running out of space. Okay. So this part is not that necessary to do, but it helps you understand like where this is coming from. Why 20? That's because it is. I believe, right, it's because decibels is in 20 log. It's in decibels, yeah. So decibels result in 20 log of this fun stuff. And remember the properties of logarithms. Multiplication splits into additions and division splits into subtraction. So this whole thing can be expressed as 20 log of 5 plus 20 log of JW minus 20 log of JW over Z over 1.5 plus 1 minus 20 log of JW 17 plus 1. That is what we are plotting. Obviously, this is not fun to plot, but it does give us a it does give us some information. So, how do we plot this? Whenever you see JW, oh sorry, how did I do this? Okay. So if we start at, let's suppose that our omega is going to be 0, right? As we approach 0, we can't actually have it be 0. What are we going to get? We're going to get 20 log of 5 plus 20 log of 0 coming in from positive direction minus 20 log of 1 minus 20 log of 1. What's log of 1? Log of 1 is 0, right? So those two go 0. This trends towards infinity. Does W always approach 0? It makes it easier. You could do 0.0001, but we're not actually calculating it. We're seeing how it's going to act at this point. Would all Bode plots follow the same format as this question, just different algebra? Correct. So if I pull out the thing there, the practice midterm here, you'll see this one here. H2 is equal 1 over 0.06 JW plus 1. You can convert that. 1 over 0.65 JW plus 1. Same thing, just JW. It's going to be in algebraic terms that you can convert to one of these. Okay. So, what this means is we have one term here as we're approaching 0. This means that we are going to be increasing at a rate of 20 decibels usually. So that's what this means. We have 1 plus 20 log 0 minus. This means that as we start from 0 going to the right, it's going to be increasing by 20. You'll see what I mean as I draw it out. Let's do as W approaches 1. What are we going to get? We're going to get 20 log of 5 plus 20 log of what's that? That's going to be 1 minus 20 log of 1 over 17 plus 1, or that's going to be 1.5 plus 1 minus 20 log of 1 over 17 plus 1. The slope is 20 because of this. This 20 means that it's going to have a slope of 20. This is just something that you just need to remember, really, doing Bode plots. Will it always have a slope of 20? Yeah, pretty much. Your slopes will always be some multiple of 20. And you'll see that in a bit. If, say, we had 2, say if we had a, so it's not a constant, if it's not a constant, so if it is not a constant, so it's just 20. Yeah, it's just this in front, which is always going to be 20 because we're working in decibels. Now, suppose that we had an extra one here. We had an extra term here that goes to 0. This means another 20 decibels. So our slope would be plus 40. We just count the terms left over. These ones are 0, so they don't count. Yeah. Okay, so what happens when our omega... What about the first one? We'll show that in a bit. Because we can't really calculate what happens at 0, so we just sort of ignore this part for now. But at 1, what happens at 1? This is roughly 1. We're going to do our engineer approximation. It's close enough to 1. And this one here is also roughly 1. What is log of 1? That's 0. So all of these terms go to 0. So at 1, we are going to have 20 log of 5. If you put that in your calculator, that's 14. So this is sort of like an IVP sort of thing. Our IVP is that at W is equal to 1, it's going to have 14 decibels. Now, we're going to do our third one. W is equal to infinity. And we're going to get 20 log of 5 plus 20 log of, that's going to be of infinity, minus 20. Now, what happens at, wait. I look at my notes. I think I messed something up here. Are these just individual test cases? Yeah. Pretty much. Oh, no, this is right. Okay. So it's going to be 20 log of infinity minus 20 log of infinity minus 20 log of infinity, right? Well, these two cases cancel out. we're left with 1 minus 20 log to infinity. And this tells us as we go to infinity, we are going to have a slope of negative 20 decibels. So let's just review what we know. We're going to start with a slope of 20 decibels. We're going to end with a slope of negative 20 decibels. Frankly, and I'm going to be completely honest with you, this whole part here, you really don't need to do. You really do not need to do. Same with this part down here. But it helps you get an idea of what we're doing. What's going to happen. So now let's pull up the Bode plot. Why does a 20 log of infinity not go to 0? It does. It does. No, it doesn't go 0. Log of infinity is infinity. Yeah, there's a chart you could memorize, but frankly, you don't need to. So when you write 20 decibels, is it like a constant? No. Here, let me show you. We'll go on to the Bode plot, and this will make a bit more sense. So the rules regarding these terms is going to be that this term kicks in at omega is equal to 0. So this means start at omega is equal to 0. Suppose we're given a quadratic in the denominator. Do we just factor it and proceed the same way as this? Yeah. And here it starts at z. Okay, so what does this mean? We are going to split this equation into zeros and what's the other term? Well, I forgot. Poles. So our numerators is going to be zeros. Actually, let me use this part. 0. And these are going to be poles. And we're going to draw it at these points. So our 0 here on the top starts at w is equal to 0. So all off to the right. Okay, wait. So our 0 is going to be at 0. Our poles is 1.5 and 17. So the rule is that zeros pull the graph up and poles bring the graph down. We can sort of see this here, as I showed you here. These two were poles, so they're in the denominator. They're bringing the graph down. This here was a 0. It's bringing the graph up. So we start at 0. We start at w is equal to 1, and we're going to draw our 0. So our 0 brings us up by 20 decibels per decade. So that's from 1 to 10. It's going to bring us 20 decibels. Sorry, I should have thought to myself how to teach this a bit better. I'm a bit over the place. But I suppose that's how it is. So this is how our 0 is looking like. Whee! There you go. So this is our JW. JW. Can you explain the line real quick? Yes. So this is a slope of 20 decibels. Our zeros bring up the graph by 20 decibels per decade. That's what it means. And it starts, this line starts at omega is equal to 0. However, when we get JW, it's going to be 0 decibels at W is equal to 1. Because you remember, so we had 20 log of JW. at omega is equal to 1, it's going to be just 0. However, the slope is going to be 20 per decade. So that is our 0 here. It pulls us up by 20. How about our poles? Remember, our poles start at z, in this case, 1.5. So let's start with, let me give these different colors so I can show them differently. So let's start with our pole of 1.5. So we're going to go W is equal 1.5. So this is 2. This is, oh, sorry. 1.5 is, this is 2. So 1.5 is going to be around here. We're just going to linearly approximate. Close enough. That's what Bode plots are. They're close enough. So magnitude is 0 at 1.5. It doesn't kick in until we reach this point. Once we hit this point, it's going to go on a slope of negative 20 decibels because it's a pole. So in 1 decade, here, this is 20. It's going to bring down by 20 decibels. In 2 decades, so this is 200, it's going to pull it down by 40 decibels, and so on and so forth. If some part of this feels a little confusing to you, feel like genuinely do say something, because Bode plots can be a little bit difficult to wrap your head around. So that's what your graph is going to look like here. And now we are going to do 17. Same concept as 1.5. You might need more space. I know, it gets ugly. It gets ugly. So now we're going to do 17. You know this is negative 20 dB. And there's the pole. So for poles, do they represent the spot where they go down? Yes. This number here represents when it starts to go down. It's the same with zeros. So if I had, say, a 0 that's 6, then I would go to 6. It's a 3, 4, 5, 6. So here. And then it would start pulling upwards. Pole and zeros just represent when they start pulling up or down. It's just that specifically, if you have a pole or a 0 that starts at 0, it gets a little weird because it can't start pulling up at 0 because we're working in logarithm. There is no 0 in logarithm. So we just sort of put the 0 point at W is equal to 1. Let me emphasize that here. If a point is equal to 0, so if starting point is 0, h of 0 is going to be, or h of 1 is going to be 0. So that's going to be, how do I write that a bit nicer? Omega is equal to 1. H of W is going to be 0. So the 5 in front does not affect the line. It does, but we do that at the end. The 5 bumps everything up, the whole graph up by, not 5, but by this amount, 14, right? Because we have 20 log 5, not 5. What's HW? That is our equation here. HJW. So basically what I'm saying is if you have a 0, if you have a 0 that is 0, if you have a pole that is 0, that starts at 0, then the magnitude is 0 at omega is equal to 1. Otherwise, if it is not 0, then the magnitude is 0 at wherever that point is. I hope that makes a bit more sense. Because remember, we cannot have zeros in logarithms. Logarithms don't have zeros. That's not allowed. Okay, so we have our 0 here, we have our pole here, and now we're going to do our 17 pole. So we're going to have at 17, so this is, where would that be? That would be around here. How can I pull my life together? It's too late, brother. So this is 17. Omega is equal to 17. Here, let me write that. Omega is equal to, what's that? Omega is equal 1.5. And omega is equal 1. And once again, it's a pull, so it's going to be pulling down. In 1 decade, you're going to be here. In another decade, you're going to be over here. So let's draw the line. That's going to be line over there. And then line down here. So here is our individual zeros and poles. And now we need to combine it into a singular equation. How do we do that? We just add everything together. So I'm going to be using 0 for this one. We literally just add up these graphs. So this is going to be 0 at this point. It's going to increase until here. What about the 20 log 5? We'll do that afterwards. I don't know why Fairnaz, as from what I've been told, Fairnaz wants you to do every single step. I'm not particularly a fan of it, but you need to do it this way, in this order. Okay, so everything else is 0, so it just follows the plus 20 dB until it hits this point. And at this point, look here, we have pulling up by 20 decibels, and we have pulling down by 20 decibels. What does that mean? That means a difference of 0 decibel, because 20 minus 20 is 0. So we keep on doing that until we get our second pull. And now, at this point, we have 120 pulling down, another 20 pulling down, and we have 20 pulling up. What is the change here? It's going to be minus 20. So once again, we're going to get our thing here, and it's going to go down like so. And we can annotate the graph here. So it's going to be plus 20 dB, 0 dB, plus 0 dB, and it's going to be minus 20 dB. And now we put in our constant here. That is our 14 decibel. And we raise the entire graph by 14 decibels. So our final graph, so this is going to be so our final graph is going to be raised by 14 decibels. That's, I'm going to round that close enough to 20-ish. Again, I'm rounding. Don't do that on the test. Going to look a bit like that. Plus 14 decibels. And now you have drawn a Bode plot for the magnitude. Are there any questions? Because I know that's a lot. Can you explain how to get the red line shape again? Yeah, so we started with the black line here. We started with the black here. And we did at that point, we did not consider this part here, this 20 log 5. When you put the 20 log 5 in front, that boosts the entire graph by 14 decibel. Why does the black line go up? The black line goes up at this point because the change here is 0 decibels. 0 decibels. 0 decibels. And the change here in the blue part is plus 20 decibels. So what's 20 decibels minus 0 decibels minus 0 decibels? We get a positive change of 20 decibels per decade. This is all working in decades. And let's see, why does it level out at 1.5 to 17? It levels out at this point because if it's a little bit messy to look here, but at this point, we have minus 0 decibels. We got minus 20 decibels. You see this is pulling down. And we still have our 0 pulling up, plus 20 decibels. Add this all up, you get a change of 0 decibels. Let me try and erase this, getting in the way. There you go. So here. And at this point, we get plus 20 decibels. We subtract 20 decibels, and we subtract a further 20 decibels. Oh. Let me try and put this all up so it's a little bit clear to see, because this is sort of all over the place right now. I should have thought about this beforehand. So all of this adds up to a change of 0 decibels. This here adds up to a change of minus 20 decibels. And here it's going to be plus 20 decibels. Subtract 0 decibels. Subtract 0 decibels. Adds up to plus 20 decibels. Should have used the dotted lines. Yeah. So it only changes at W is equal 17 because it's 2 negative 20s against 1. Correct. And likewise, if we happen to have, say over here, if we happen to have another plus 20 decibels, this would be plus 40 decibels. We don't, but if we had to, it would be plus 40. We just add it up. That's it. We add up the slopes. And so we raise by 14 decibels because this is 20 log of 5. Anything else? Okay, I think that's all the questions for magnitude. But we're not done. We have to do the phase. Aren't you excited, guys? Don't worry. Actually, the phase is actually easier. Do we need to draw the constant 20 log 5? Here, 14. It raises this up 14 decibels. There you go. Do we have to do all the steps on the semi-log paper or just the final one? I have been told by someone who attended Fahrenheit that you have to draw each one of these lines. I don't know why. It's stupid in my opinion, but that's what I've been told. So just for completionist's sake, I would recommend that you draw everything here. Yes, I'm gonna be completely honest with you. If you didn't have to do that, you would the amount of work you had to do is much smaller. It's broken down in the midterm. You get a graph for each line. Okay, that's good. I did not know that. So yeah, if it explicitly asks you to do that, you have to do it. You have to be able to draw each one of these lines. Okay. So, is this question from a past midterm? This is the practice midterm. It's given to us on the D2L. Is Fahrenheit running the course? I'm confused. I think so. I would have to check. I really don't know. Listen, all I know is that I've been told that you have to draw all of the lines. You can't just draw the final graph. I know, I also just drew the final graph when I first did it, but I've been told you can't do that. So, we have a lecture tomorrow, right? Or am I tripping? No. So you have a lecture on Wednesday, so you can go there and ask her. But yeah, I don't know. So now we have to do phase. So for phase is actually easier. I'm going to be completely honest with you. Phase looks like this. So our phase is going to be what's that? Okay, so there's two rules for phases. If you have JW, this turns into a 90. If you have 1 over JW, so if you have JW as a pole, you have negative 90. Now, if you have JW over Z plus 1, that's going to be a tangent of negative 1 of omega over Z. And if it is in the denominator, it's a subtraction. So these are the 4 rules you need to know. Pretty simple. So our phase is going to be, so we have JW on top. Let me just copy paste our equation for those who forgot already. Can't blame you. So here's our equation. Our phase is going to be 90. We ignore the 5. In the phase, we ignore this 5. Minus tangent inverse of omega over 1.5 minus tangent inverse of omega over 17. Now, I said before that you can sort of skip this stuff here. You cannot for phase. So phase, where omega is equal to 0, or approaching 0, you're just going to get 90, right? Because these tangents go to 0. Oh, sorry. No, this is equal to, what's that, 1? Okay, 0. Oopsie, 0. Yeah. It's going to be 90 minus 0 minus 0, right? Because tangent inverse of 0 is 0. So we know that our graph is going to start at 90 degrees. What about when it approaches infinity? Why is W 0? We're just testing the ends of the graph. So we're testing if we're going towards 0, what is the phase going to be? If we're going to infinity, what is the phase going to be? That's all we're asking here. So this is going to be 90 minus, yeah, we're checking the graph's behavior. So it's going to be tangent inverse of infinity minus tangent inverse of infinity. And that goes to 90 minus 90 minus 90. Negative 90. So we are going to be starting the graph at 90 degrees. We are going to be ending the graph at negative 90 degrees. Let us mark that on the graph here. Just so we don't forget. Now, so how this works, it's very nice. How this works is we take our z again, so this is 1.5. So our points, our poles here, we have 2 poles, which is 1.5 and 17, right? We have no zeros. We ignore this 90. It's not a function, it's just a constant. Is the tan invasion part of a trig identity or something? I don't know. You just remember it, you know? Wait, which tan equation? You mean this one? Or you mean these ones here? The ones on the left? Yeah, you just gotta remember it. So we have no zeros here. So this equation, we have no zeros, and we only have poles. So how does this work? So how this works is we go to 1.5 like we did before. This is 2. So this is going to be 1.5. And what we're going to do is we're going to create a span of a decade. So this is our lower bound. This is our upper bound. So this is 0.15 to 15. See what we're doing here? I'm going to label this one here yellow. And so, how these pole graphs are going to work, I did send a screenshot of this just above a while back, but you might be a little hard to find. So before 0.15, it's going to be 0. Afterwards, it's going to decrease at a rate of 45 per decade. So that's going to go all the way down to negative 90 until you reach 15. Until afterwards, it flatlines. So you can probably see the behavior here. So it starts at 0, it hits the lower bound, it starts decreasing at negative 45 degrees per decade. And then once it hits the upper bound, it goes back to not changing at all. And we repeat this process with 17. So here's 17. We're going to do 1 decade above, 1 decade below. And we're going to have our line here come across like that. It's going to decrease once again at a rate of negative 45. So after 2, it's going to end up like that. And then it's going to continue on flatlined. Again, this is negative 45 degrees. Are you sure? Yeah. Again, if you happen to have a 0, then it would be increasing by 45. But we do not. We only have 2 decreasing. So, again, we just add this up. So, at this point here, what's happening before this point? We have minus 0 degrees, and we have minus 0 degrees. So it's not going to change at all. What happens at this point? Here we have minus 45, but we have minus 0 here. Once again, we're going to break it up. This point, and I'm just going to go ahead, do this point. Could I use a different color than yellow? Might be a little hard to see. This is going to be minus 45 degrees. Minus 45 degrees. This is still minus 45 degrees. This is going to be 0 degrees. And then 0. Why did it change on 0.15 and at like 115? So that's 150, not 115. That's just how phase works. So our pole here is 1.5, right? So what this means is from 0.15 to 150, you're going to have a drop of 45 degrees per decade. And likewise, this means that from 1.7, so 1 decade below, to 1 decade above, that's 170, we're going to have a drop of 45 degrees per decade. Outside of that, it's not going to be. It's 45, negative 45 every time for poles. Yes. And likewise, if you have zeros, it's going to be plus 45. So negative 45 degrees per decade pole, and plus 45 degrees per decade for zeros. And so what do? We just add it up. So this is going to be 0 degrees. This is going to be minus 45 degrees per decade, minus 90, minus 45, and then minus 0. Graph it out. No change here. This is going to decrease by 1 decade. This is going to be decreasing by 2 decades, all the way minus 45. And then this decreases by 1 more decade to 0. That's it. It's that easy. Any questions? Oh, good catch, good catch, good catch. So that should be 15. Thank you. Why is it 45 degrees per decade? You just gotta memorize that. I'm sorry. It's just going to be memory. Let me just highlight all of this here as something you need to remember. So W is equal 0 and W is equal infinity helps us find the endpoints. Correct. The only reason why we do this is to figure out where this starts, where this ends. So in this case, it starts at 90, it ends at 90, negative 90. Because it's hard to tell where it's going to go to just based off this. Because this isn't exactly 1 decade, this might not be exactly 1 decade, so on and so forth. This just helps you figure out, okay, at infinity, I should end up with negative 90. It's a good check on yourself to make sure that you're not insane. So this is the hardest Bode plot that you're probably going to get. If you can do this, you can pretty much do all the Bode plots. I'm not sure of any Bode plot that's going to be more complicated than this, that you need more information for, that I haven't taught you. Why did they make it much longer and harder? Because they hate you. They gave 3 Bode plots for the sample one. I believe it's 4. Yeah, it's 4. 1, 2, 3, 4. And a phaser. Will we come across Bode plots with like JW squared? You may. And it's just going to be the same thing. So instead of having 1 0 at 0, you're going to have 2 zeros at 0. That's it. And instead of no quadratic Bode plots, okay, nice. But the concept's the same. Just treat it as a separate root, and you get the correct answer. Okay, I think that's good. Maybe we should move on to second order RLC circuits. Or is there any other questions that I am missing here? Let me just save this 1 second. Midterm tutorial. There you go. So just to make sure, yeah, question. When you wrote the tan inverse stuff, yeah? Is it always going to be in that format? Correct. Yes. It's always going to be, you're just taking this and turning into that. It's not. Let me move that down so it can fit on the same page. So JW term is always 90, correct. So here, JW turns into 90. 1 over JW turns into negative 90. And likewise, JW over Z plus 1 turns into tan inverse. 1 over that is going to be negative tan inverse. Midterm, do we just have to derive that JW? You don't have to derive that. You have to memorize it. No, you do not need to show your work. This is, if you want to really understand where it's coming from, it is coming from magnitude. If you remember, it's phasor. So all of the magnitudes here is, what do you call it? Is phasor, right? So treat W as some variable that's just going to be W with a phasor of 90. 0 Bode plot work will be shown. And likewise, this tangent is just the phasor part of it, right? So if you actually think back to all the way back to what's that, linear algebra? If you wanted to find the phasor of it, if you want to find the angle between the vector formed by the complex number, yeah, you do tangent inverse of W over Z of the what's that? Yeah. Don't think too hard about it. Just memorize it, you know. Deriving it on the test is going to be far harder than just memorizing that JW is 90 degrees. And you do not need to show that. Real quick, how would you draw this amp in your way? Okay, we'll just do a little detour here, and then we'll go into R2 circuits. Just showing how I would draw this. This here, for example, you would have your connection here, connected by a resistor. And that is also going to be connected through a dependent that's connected to ground up there. Like that. Okay. So second order RLC. Oh, do you want me to keep that up for now? Second order a screenshot? Yeah, sure. Second order RLC. So I have two second order RLC circuits set up. Do you guys want to do the one on the practice midterm, or do you guys want to do a harder one? All right, let me see. Harder? The harder, the better. All right, perfect. I'm getting a little suspicious, you guys know. Okay, I don't even need to be suspicious about that one. Okay, let us do this one here. Oh, so we are going to have 8 volts here. Going to come up into a resistor of 2 ohms. Comes down here into a 2 ohm resistor that goes into another voltage source of 2 volts. And it's going to be connected by a gate that closes at t is equal to 0. And then you are going to have an inductor. And obviously a capacitor in parallel. This is our circuit. And the question is going to be plus minus VC is equal to, This one, Honestly, I was told it was a little hard, but I did whatever. Anyone remember the guy who lied about being from an oil mogul company family? Was that like was that in the server? Like, huh? I don't remember that. Anyway, so this is our circuit. Oh, I forgot. This is going to be 2 Henrys and 1 Faraday. Doesn't really matter. The amount of Faradays or Henrys shouldn't make it harder or easier for you. If you have a calculator. God bless, I love calculators. Okay. So how do we do this? Remember, if we are trying to find voltage, we use KCL. If we're trying to find current, we use KVL. We use the opposite, right? So we're trying to find the voltage here, so we're going to use KCL. And, oh, I forgot to mention this is ground. Doesn't really matter. So this hole here is a singular node. And let's define, this is also VC, right? Because this is ground, so that's going to be VC. But doesn't it also depend if the circuit is series or parallel? Correct. You would get a different answer if things were in series, not parallel. Oh, like what you would use? No, the method you use wouldn't change as far as I'm aware. Yeah, I don't see why that would change. Let me see. Maybe I did do that. Let me see how I solved another one, like the one of the. No, yeah. You started saying that? Because the one on the practice midterm, for example, the one on the practice midterm here, it asks you to find the current, and it's in series. You solve it using KVL. Or maybe it is like that. Maybe I think. No, I think it should be the same thing, really. Because what you're trying to find is voltage. So you use, say if you're finding voltage like we're doing here, if you use KVL, you kind of have to take an extra step to find V. It's not impossible. Like if you do KVL, you're not gonna die, right? You're just gonna find the current, and you can use the current to find the voltage. Because if you know the current, you know the voltage. You can have to do both sometimes, maybe. I can't think off the top of my head, but you might be right. You might be right. In this case, we could just use KVL because KCL because we're trying to find voltage. Yeah, first check if you're trying to find current or voltage. If you're trying to find voltage, you should probably use KCL. If you're trying to find current, you should probably use KVL. And again, using the wrong, quote unquote, wrong method, you will still get the right answer. You might just have to take a little bit of a detour. For example, if I use, it just saves time. If I do KVL here, I would find the current running through the capacitor, knowing the current, actually, I would know the current running around here, and using that, I can probably just find the voltage. But in this case, make your life easy, just use KCL. Let's do that. VC, we're going to assume that the current flows in here, like this, like that, like that, like that. Why not? So, ooh, 1 second. Wait, can I do that? Let me see. Yeah. Wait. Just making sure if I'm, yeah. So do like this. So you're going to get 8 volts. Wait. Yeah, so just assume this. So you are going to get Sorry, I'm blinking out. This is my bad. Oh, that's why. That's why. Okay, this is wrong. This is wrong. Assume going out. Remember what I said before? When you have say something like this, VC, you should always assume the current's going the same direction from positive to negative. Just to make our lives easier, we're going to assume the same thing for everything else. Oh. Man, I'm all over the place. I'm so sorry. Okay. So this is our circuit here. We're going to start with making the second order formula. T is greater than 0. I know a friend of mine is fuming right now. Actually, you shouldn't write it T is equals 0. You should write it some other stupid way. He can cry about it. I'm going to get an angry DM very soon. Okay, so this is at T is greater than 0. And we are going to find VC at T. That's different. T is equals 0 plus is different. So we're going to assume that all the current rolls down. The direction doesn't really matter except for this one. This one has to be in this direction. It should flow from positive to negative. So what are we going to get? We are going to get, let's start from left to right. So this is going to be VC minus 8 volts because we're passing through the negative end of a voltage source, minus where we're ending up, 0, which is ground. We're ending up in ground, so it's 0 volts. Over a resistance of 2 ohms. Now we do the second line coming out of VC. That's going to be VC minus 2 volts because we're passing through the negative end of a 2 volt input source. And we're ending up at ground. Over 2 ohms of resistance. Plus, and here we can't really figure out this, so it's going to be IL plus IC. The current flowing through the inductor and the current flowing through the capacitor. Now, we are trying to find voltage, not current. So we need to get rid of these ILs. And wait 1 second. Yeah, I got the angry DM. This is all equals 0. And so these zeros go nothing. What are we going to get? We're going to get 1/2 of VC minus 8, minus 8 over 2, that's 4, plus 1/2 of VC minus 1, plus IL plus IC. Now, remember the formulas. So the formulas we need to remember is for inductors that the derivative of, let me check, yeah. So L times the derivative of the current over an inductor over time is equal to the voltage over the inductor. And likewise, the capacitance times the voltage passing through a capacitor, derivative of voltage passing through a capacitor, is equal to the current over the capacitor. And remember the inverse of that. We could just integrate both sides to get the inverse, the second set of formulas. That is going to be L times IL is going to be equal to the integral of VL. And likewise, C of VC is equal to the integral of IC dt. That's correct, right? Yes. So, using this, we can now replace our IL and IC. IL is going to be equal to 1 over L times the integral of VL dt. And our IC, we could turn that like this, into C of dVC over dt is equal 0. At this point, This is all calculus. We can combine these terms like that. And because we have an integral in here, we want to derive this entire equation because we don't like integrals and derivatives in the same equation. So we take d over dt of this entire formula. What do we get? We get vc prime, we get v prime. Our constants go to 0, so that's going to be minus 0, plus 1 over L of v plus c of v double prime is equal 0. Remember that the derivatives of constants is 0. I'm saying this because I am stupid the first time I did this question. And so we have produced our second order formula. Is anyone confused about how we got to this point? Well, let me just annotate here. So 1 v is equal question mark turns into Kirchhoff's current law, and I is equal question mark is equal Kirchhoff's voltage law. And then second one, create the equation EQ. Third step is that we apply these. And then fourth step, we simplify. Any questions? And we're going to rewrite that again. Plus 1 over L V, this is going to be V prime. Plus 1 over L V is equal 0. Would they ever put a capacitor and inductor in series and make you write an equation for that? Correct, yes. Are we sure this is the hardest question? No, this is a harder question. It is not the hardest question. In my opinion, anyway. Frankly, they're all about the same complexity. There's nothing overly or... I don't think there's going to be any surprises, you know what I mean? Hardest would be like where you do both KVL and KCL find the equation. Maybe. I'm not sure of any... To be honest, I haven't done very much second order circuits, so I don't know any like that. But I would reckon that this is probably going to be about the scale of how difficult it will be on the midterm. I can't see them throwing something insane at us. Okay. Third order circuits, let's go! God, I love Laplace. Sorry, 1 second. Okay, I'm back. Okay. So now we have to find our initial conviction. Conditions, not convictions. I'd be very concerned. Where is it? Yeah, our initial conditions. I said it again. So our initial conditions are going to be at t is equal 0 minus and at t is equal 0 plus, right? No confusions about that. Hi, back. Look at you. Okay, so at t is equal 0, and I'm going to draw this fast because I really don't care. You're going to have one resistor. You're going to have the inductor, which turns into a short circuit. And you're going to have the capacitor. This is 2 ohms. This is still going to be 8 volts. 8 volts? Yes. Okay. Don't we find our characteristic equation first? You can. It doesn't really matter. Sure, let's find the characteristic equation first. So, we have, what's that? Our capacitance is 1 farad, so we're going to have V double prime plus V prime plus 1 over 2, because our inductance is 2, if I'm correct. Yes. V is equal to 0. I am too lazy to do the math myself. I already know the answer. It is going to be V as a function of time is going to be e to the negative 0.5 t times c1 sine of half of t plus c2 cosine of half of t. And question for y'all, what amount of dampedness is this? That's correct, even though nobody replied. It is underdamped. Remember that e to the at plus e to the at is critically damped. E to the at plus e to the bt. Well, this is going to be t e to the, you get the idea. It's going to be c2, c1. Do we need to memorize this? Yes, you do. You absolutely do need to memorize this. It's going to be c2 e to the bt, where b is not equal to a. This is overdamped. They're going to test that? They will. They can, and usually they do. What do these terms even have anything to do with solving the equation? Not really anything. You just need to sort of memorize it. They produce different patterns in the test in measurement. I believe, if you remember doing the lab, I might be wrong on this. I will probably get angry DM if I am wrong. Is that critically damped? If you looked, remember when you're doing the lab, critically damped will look like this. Actually, I'll write down here. So critically damped will look like this. Overdamped is going to look like this. And then underdamped is going to look like that. Isn't half of v prime in the equation? That is our differential. Wait, what? No. Because of resistor. Yeah, that produced our v prime. Oh, the thing is, we had two of them. If you look here, we had half of VC and we had another half of VC. You add them together, it makes one VC. Will they make us draw the graphs? I do not think so. I don't think so. I doubt it. But yes, e to the at times sine of t of some bt. Oops. C1 sine of bt plus c2 cos of ct. Actually, it's the dt is underdamped. So anyone got any questions about that? Cool, I'll take that as a no. Is this just calculations for when we find the roots of yc? Yes. Can you scroll for a second? Yeah, sure. Do you want me to take a screenshot of what I've done so far? Sure. Okay, I'll take that. So that's screenshot, and this is the original question. Ignore that right side, that's just step instructions. So 3, 4, simplify. This is gonna be 5 YT. Complementary equation. Okay, awesome. So Now we need to find our initial condition so we can solve the initial value problem. Very important. So we're going to draw our graph at t is equal to before 0 and t is equal to greater 0. Is anyone confused about how these circuits are being drawn? Like where I'm getting all of this? Like how I get to drawing this point? You know what? There's people watching the recording afterwards. Why not t is less than 0? It's going to be the same as t just before 0. We assume steady state before 0. So for those who are at home watching the recording and you don't have the opportunity to ask a question, I'm going to answer this for you. At t is less than 0, we assume steady state. And recall that steady state, inductors turn into short circuits, capacitors turn into open circuits. So this is our capacitor here. Let me, oopsie daisies, what did I do? Let me draw it a bit better. So this is our capacitor. That's our voltage across because it's steady state. At time is greater than 0 or greater, we cannot assume steady state. So we have to draw the whole circuit. And of course, the gate is open at this point, so we just ignore that. Okay. So, now we need to find our steady states, or our initial conditions. So if we look at t is equal to 0, this was really simple. What's the voltage across this? It's going to be 0. Oops, 0 volts. So VC at 0 minus is equal to 0 volts. And likewise, if we look here, we can measure the current here. Is that relevant? Yes. Okay. So the current here is just the current through the whole circuit, right? It's KVL. So that's just going to be the voltage over the resistance. That's going to be 8 volts divided by 2. That's 4 amps. Therefore, our current for the inductor is at 0 minus is equal to 4 amps. And remember the behavior of inductors and capacitors. This, for inductors, or for capacitors, VC 0 minus is equal to VC 0 plus. And for inductors, I at 0 minus is equal to I at 0 plus. VC is 0 because there is current. VC is 0 because this is a short circuit. So we cannot directly measure the voltage across here like this. We instead compare these 2 points. It's a short circuit. What's the voltage difference in between a short circuit? 0. Yeah, it's parallel to short circuit. So remember these 2 equations. And I'm going to give you the word of warning here. Of what you cannot do. Don't do those on the bottom. Okay, so now we know our first initial condition, and that is that VC at 0 is equal to 0 volts. And now we have T is equal to 0 plus. So once again, we can do KVL here. Do KVL here. We are going to have 8 over 2. KVL. Sorry, KCL. That's going to be 8 volts over 2 ohms. This here, this 8 volts, 2 ohms. 2 ohms, and it's going to be 2, yeah, 2. Plus 2 over 2. Did I just assume that? Oopsie. So that's gonna be negative. Or yeah, it's actually gonna be fine. Whatever. That's gonna be negative here. That's gonna be negative there because we're passing through the negative end of it. Plus IC plus IL equals 0. Can I turn on webcam? I will not. You are not getting my live reaction. So, oopsie. We have our what's that here? Yeah. So we have IC, which we can convert into oh my god, I hate you all. We know that this is the capacitance times the derivative of the capacitance voltage, which is exactly what we need. We need this. And we know the inductance at 0 plus, the current of the inductance at 0 plus. It is, we calculated here, it's 4 amps. And obviously we can calculate this, it's going to be -1, that's going to be -4. And what do you call it? Our capacitance is 1. Therefore, you get -5 plus 4 plus VC prime is equal to 0. VC is equal to 1 amp, or 1 volt second. Generally, when we do second order differential equations, the questions will ask for something in particular, like dt, dv over dt, or di over dt, right? Yes. So it will always ask, hey, what's the current, or what's the voltage over this at time, at some time? Can you make an equation for it? That's what they're asking for. And to do that, you get second order differential. To solve the second order differential, you need to know the initial values. And that's what we're solving here. Yeah. So now we can input this into our differential equation. This is just IVP. Wait, sorry, but how did we get a different KCL by using the same circuit as the one in the beginning? Because this occurred at time greater than 0. So we are stuck. We actually got the same exact formula here. If you look here, we have this exact formula here. The only difference is that we get to carry over this current here into here, right? Because IL at 0 minus is equal IL at 0 plus. So at exactly t is equal 0 plus, we can carry over this information that we solved in the steady state before 0 plus. Yeah, okay, there you go. So I didn't exactly annotate this well, but all of these calculations can only work at 0 plus. If it is at t, we could not bring this value over, and we would be stuck with the differential equation. So this solves for VC at, yeah, I really should have written this out. My bad gang. This here is at 0 plus. We can only solve for exactly at 0. Not calculating for VL and IC in steady state. Yeah, you can't. Because if you have steady state, then the voltage across the inductor is 0, and the current across the capacitor is 0. We cannot find the derivative of it at steady state. A way to think about it is that at steady state, everything is steady. What's the derivative? 0. So it's kind of useless. You cannot find derivatives from steady state. That's an important rule. But likewise, you cannot calculate some of the initial values without steady state. That's why we do both time is before 0 at 0 minus and time after 0 plus. Okay, and now we just so step 6, I believe it's step 6 that I wrote. Oopsie. Step 6, yep. Let's move all this down. IVP. This solves for V. Oh, sorry. This solves for V. This solves for V prime at 0. And now we bring it down. Solve IVP. And now we just repeat everything that we know. So we have our differential equation here. We have our complementary solution, which is really what's important. And we have our steady states, or our initial condition. So that's going to be V at 0 is equal to 0, and V prime at 0 is equal to 1. That's going to be 1, 0 plus, sorry. 1, wait, sorry. What am I doing here? Sine at 0 is going to be 0, so that's just going to be 0 plus T2 of 1. Because cos of 0 is 1. Simplify that out. Cancel everything out. T2 is equal to 0. And now we can derive. So we know that Vt is equal to e to the negative 0.5t times C1 sine of half of t. Remember, cos is gone because C2 is 0. So therefore, V prime of t is going to be, this is going to be a product rule. Who loves product rule? I can't hear you. Okay, I guess nobody likes product rule. I see people do not like product rule. Okay, so that's going to be negative 1/2 of C1 sine 1/2 of t e to the negative 0.5t. Now what happens at 0? That's going to be 0. Oh, sorry. Cosine at 1 is going to be, cosine 0 is, okay, yeah, so that's going to be 1 over 2 t1. That's going to be 1 minus 1/2 of C1 0 1. Cancel, 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 cancel. Our initial value is our thing is going to be 1 here. So that's going to be that C1 is equal to 2. There you go. And now we can finally make our final equation. That's going to be e to the negative 0.5t 2 cosine of 1/2 of t. There is everything you need to know about second order circuits. Was that how you solved the ELE tutorial question last week? Yes, I did solve it that way. That's how you solve it. I did get 100 if you were gonna ask. Really? Crazy. But yeah, these are the 7 steps to solve second order circuit. And they're all real simple steps. All individually real simple steps. Half of it is just calculus. So if you did well in the calculus midterm, you should be fine with half of it. The other half is just ELE302. This is literally just combining ELE302 with Calculus 3. Okay. Oh, shoot. I forgot about one last thing. So, I forgot about one thing. It doesn't matter in this case, but you should do it. And that is a steady state, a final steady state. So if, say, you have, so you also have to find a steady state after infinite time. And once again, you're going to get plus, minus, yada, yada. It doesn't really matter. You know what circuit I'm drawing here. You need to find the voltage C at steady state. And in this case, it's 0. So if this was not 0, you would have to go here and you would have to append at the end of this equation your steady state. Like that. Now if, oh my lord, if you do not have any circuits in your diagram after t is equal 0, then you can just automatically assume that your steady state is 0. But if there are voltage sources, I would recommend you check, you find steady state. So it's going to be 7, find steady state as t approaches infinity. And likewise, it's 0. There you go. Are there any questions? When do we find VSS and ISS? You mean steady state? You mean as it approaches infinity? Here. So, if you do not, as I was saying earlier, if you do not have any sources in your circuit after time is equal to 0, you can just assume that steady state is 0. Because there is no voltage running through it at all. There can be no voltage drop. But if you do have voltage sources, like here, or if you have current sources, you need to find the steady state. All you need to do is draw steady state at time infinity, again. So that's going to be the same as, say, this circuit here, except these are going to be steady state. So the inductor is short-circuited and the capacitor is open-circuited. And you find what you're looking for. In this case, can you draw an example of when we gotta find it? Yeah, sure. So if at steady state, suppose at steady state, you are left with this diagram. So this is VC across. Notice there's going to be a voltage drop across the resistor. VC will not be 0. And so once you get to your solving your IVP, you have to tack on your steady state at the end. So the what do you call it? You would be doing all of this except with the steady state at the end. That's it. So we need to do another KCL for V infinity. In this case, yes, you just have to do a KCL. It's a very simple KCL in this case. Generally, finding your steady state shouldn't be hard because it's in steady state. Sorry, so your circuit is simpler. But yeah, if you do not have a voltage source in your circuit after t is equal to 0, you do not need to find a steady state. It is 0. Want to do that? That looks. Let's see. Ooh, that's funny. Unfortunately, I think this tutorial's gone on long enough, to be honest. I can try solving it and putting it in the document afterwards, but probably not today. It's already 8. I don't think you're gonna see something like that on the test, but it's same concepts, right? You're gonna find the same thing. It's the same steps, same 8 steps. Crazy statements happening in chat. So wait, when do we find V infinity? Just like I said here, so it is steady state. If you have a voltage source in your final circuit, after t is equal 0, you have to find steady state voltage or voltage infinity. Same thing. Okay, so if there are no other questions, I think we've gone over everything that really we need to. We've gone over an example of case of all this stuff.